Okay, good morning, everyone. My name is Andrae. I'm working in the Gaia Consortium, as you can probably guess. And this morning I want to give you a quick overview of the GSPPhot package, so the attempt to parameterize stars from the quote-unquote photometry. So I will first give you a somewhat extended overview of what the Gaia satellite is, what it actually does observe. And I will spend a little bit more time on that, such that you can also get a better idea what are the actual observables from the satellite, and this will also probably explain a little bit better how the parameter pipeline and the different modules are organized, because the modules follow more or less the organization of the data observables. Then I will very quickly go with you a little bit through the catalog contents of DR3, and then just coming from the big picture, how does the satellite work, what's in the data in the data archive. We will then focus on GSPPhot in particular. Okay, so without further ado, let's get started on the basic facts of the Gaia satellite. So the satellite was launched, as you may remember, in December 2013. It then took some time to fly to L2 and be commissioned there, and to check that everything was properly working, excuse me. And then the nominal mission started in summer 2014. And it lasted for 5 years, and in summer 2019, the nominal mission has actually ended. So, and since then, we are in the mission extension phase, which will probably last until the first quarter of 2025, when the satellite essentially runs out of fuel. We have had a couple of data releases in the past years. Most recently, we had the third data release in June last year, which contained the data from the first 34 months of the operations. So not yet the full data from the nominal mission. That will come in data release 4, which is currently scheduled as not before the end of 2025. So, and this will contain all the data from the nominal mission. And then data release 5, where the data is not yet clear, data release 5 will contain all the data, including the mission extension. Okay, so what does Gaia actually observe? So what you can see here, this is a picture of the focal plane of Gaia. So all the CCDs, when they were constructed in the lab. And just to give you an idea of the dimensions of this focal plane, so the length is about 1 meter and the width is about 40 centimeters. So this is quite large. And so what happens here is, because of the Gaia satellite spinning, a source enters, so a star or a galaxy or whatever, enters on the focal plane on the left, and then it crosses the focal plane towards the right. And given the size of the focal plane and the spinning period, it takes the star roughly 10 seconds to cross this focal plane from left to the right. So while doing that, it crosses various types of CCDs. So let's just very quickly go over them. So the first 2 columns of CCDs here, these are the sky mappers. And what they essentially do is they do source detection. They detect, okay, here is a source of light, and then the onboard software decides, is that source of light bright enough? Do I want to observe that? And then in the following CCDs, the observational windows get allocated or not. If the source is too faint, then obviously not. And then we have this huge block of CCDs here, which is several CCDs long. So a source traveling across that, let's take a lower one, across these CCDs accumulates a lot of signal to noise. And these are the so-called astrometric CCDs. So this is where the position measurements are happening, where the parallaxes are measured, proper motions, and the apparent G magnitude. Then after the astrometric CCDs, a star would continue to cross these two columns of CCDs, and these are the BP and RP CCDs, and those will be the main protagonists of this talk. I will get in a little bit more detail on the next slides. And then if your star is in the upper half of the focal plane, it will also cross this block of CCDs here, and these are the RVS CCDs. Again, you have a row of 3 CCDs here, and as I said before, in the astrometric field, the goal here is to accumulate signal to noise. Okay, so, but as I said, the main protagonists of this presentation are the BPRP CCDs. So let's talk about them a little bit more. So these are dispersed, so these observe dispersed spectra, and they use prisms. And here you can see these prisms in the lab. And there are 2 of them, one for the blue wavelength range, one for the red one. They're called BP and RP, but both the community as well as we in the consortium got lazy in recent years. So we are just it's sort of calling them just XP has sort of established itself as the name for this combined set of data. Now here in the bottom left, I'm showing you one example of these BP-RP spectrum. This is for a solar twin. This is this nearby star 18 SCO, which is fairly bright, 5th magnitude for Gaia. This is fairly bright. And here you can see this is actually 2 spectra. Yeah, because you have 2 rows of, so you have 2 CCDs, you have 2 prisms, so you get 2 spectra. You get the BP spectrum here in the blue part of the optical range, and you get the RP spectrum in the red part. Yeah, so, and what you can see here is the BP-RP spectra, they really cover the optical wavelength range, and they go a little bit into the very near infrared. As you can also see here, I intentionally plotted the spectrum as histograms. The resolution of these spectra is fairly low. This is what is shown here on the right-hand side. This is the spectral resolution as a function of the physical wavelength. This is BP, this is RP, and we just look at the blue curve here, which is the mean spectra. This is what MS means, the mean spectra. I will explain that in a second. And as you can see, the spectral resolution for BP is between 20 and 60, and for RP, it's between 50 and 30. And I forgot to mention that all the papers, so this is explained in this paper here, because we published a large number of papers as part of DR3, and it may be difficult for you as users to know exactly which of the many papers to look into. All the paper references that I have in my presentation are links that you can click on, and it will take you to exactly the paper that I had in mind when I was doing this reference. Okay. So yeah, I was talking about the mean spectra of BP-RP. So what does that actually mean? So these XP spectra, so as a reminder, BP-RP is XP. These are time-averaged mean spectra of the roughly 40 epoch spectra that every source has in Gaia Data Release 3. So we have to somehow combine them in order to accumulate the signal to noise. And obviously, that's given that this is a time averaged mean spectrum, that may not work if you're focusing on variable stars like an RLI or a Cepheid, where you have substantial variations in the temperature and the other properties of the star. They're just averaging all the spectra that you have observed over 34 months just doesn't make a lot of sense. But for the vast majority of stars which do not show large-scale variations, that is perfectly fine. So we have one problem though, when we want to combine all these spectra, is that the epoch spectra, the sampling of the pixels changes every time. And the reason for that is very simple, because if I go quickly back to the CCD, to the focal plane, the same star may once cross the CCD, the focal plane over this CCD row, and next time it may cross over another CCD row, depending on the orientation and scan direction of the satellite. So that means the geometry will be different between two transits, between two epochs, and thus the dispersion of the prisms will be slightly different. And even if you cross the same CCD row twice, the instrument has aged. I mean, L2 in space is a very harsh environment. The instrument ages with time. So also the dispersion relation of the prisms change over time. So even if you cross the same CCD twice, you still don't get the same wavelength sampling. Yeah, so as to say that in a somewhat polemic way, no two epoch spectra of any two sources will ever have the same pixel sampling. Yeah, and as a result, we cannot just stack these epoch spectra. If we would just stack the epoch spectra, we would lose a lot of information. In particular, we would lose wavelength resolution. So instead, what our colleagues are doing is they need some kind of continuous function that they can evaluate at whatever pixel the epoch spectrum is asking for. And the particular choice for this continuous function has been a basis expansion. And this is the reason why the XP spectra come in this slightly strange format. So the basic format are these expansion coefficients. So you get 55 coefficients for BP and another fixed 55 coefficients for RP. And they are called XP continuous in the Gaia archive. Yeah, because again, this is a basis expansion. This represents a continuous function that you can evaluate at any pixel position, whatever your epoch spectra are asking for when you want to combine them. Another data format that you can obtain from these continuous function is, of course, you can sample these continuous functions to produce actual spectra, meaning flux as a function of wavelength or pixel. And you can do this in two different ways. You can first do it on the internal system. This is not publicly available, but in principle, you can do that. And you can do it on the external system. That means physical wavelength versus physical flux. And this is called XP sampled in the Gaia archive. And on the next slide, I show you the difference between the two. Sorry, this was actually an animation, but due to technical problems, the animation isn't running. But on the left-hand side, you see this is a solar analog spectrum, which has no extinction. Yeah, and on the left-hand side, you can see the internal sample spectrum as that's essentially the instrument flux versus wavelength, and you can see BP and RP separately. And then in the external spectrum, that's the same star. Yeah, it's just the underlying XP coefficients have been sampled in two different ways. And on the right-hand side, in the external spectrum, you get actual physical flux versus wavelength. So mainly the difference between left and right is that on the right-hand side, BP and RP have been combined into a single spectrum. And that spectrum looks like a proper SED as you are used to, meaning the main difference between left and right there is that on the left, you have the instrument throughput, whereas on the right-hand side, this has been taken out. Yeah, okay. So, and the fourth format of XP spectra is that you can use these XP coefficients that cover, if you remember, roughly 300 nanometers to 1050 nanometers. You can use those to synthesize narrowband photometry, something like the SDSS photometry, the typical UBVRA photometry can all be synthesized from XP, and that's an alternative way of using the XP information. This can also be done using the Gaia XPy Python package. Again, that's a clickable link. If you want to know more about Gaia XPy, just click on it. It will take you to the website of Gaia XPy. Now, which of these So if you want to work with XP spectra, which of these four different formats you choose is essentially a question of feature selection. Yeah, and that depends. There's no generally correct answer that this format is always better than all the other formats. No, which format works best depends on the specifics of your scientific application. And you have to reassess that each time that you come with a new project, right? And to some extent, this is discussed also in this paper that we wrote after the data release. Okay, so just to give you an idea of these BPRP spectra, how do they look like? And for the purpose of GSPPhot, for the context of this talk, we will always be in the internal sample spectra, yeah, because this is what we are working with internally. So on the left-hand side, you can see different stars. So these are all real stars. These are not models. As you can see, there's one outlier hiding here in the back, which has a different shape of the spectrum than it should have. Yeah, so these are all real stars, color-coded by their temperature. And you can see here very beautifully how the temperature changes the shape of the BPRP spectrum. As you would expect, hot stars have more flux at shorter wavelength, whereas cooler stars have more flux at the longer wavelength. What you can also see here is that in general, the resolution of these spectra is quite low, so you usually will not see any absorption or emission features in the spectrum. However, there are exceptions. And here you can see such an exception that for very cool stars, you see molecular absorption bands here and here. So the right panel is what should have been the animation on a few slides before. That didn't work. So here you just have the summary picture of that animation. And this shows you for solar-like stars, what is the impact of the line of sight extinction? How does the line of sight extinction change the shape of the spectrum? And here again, you can see what you would expect. You see that the flux is in general reduced the higher the extinction is. But shorter wavelengths are more stronger affected by dust extinction than longer wavelength. So you not only see the dimming of the flux, you also see the reddening here. And also when you compare both figures, you can sort of already guess what one of the main limitations of XP spectra will be, as mainly optical low resolution spectra, temperature and extinction will be highly degenerate. Yeah, so you can increase the temperature of a star and increase the extinction at the same time, and the effects will sort of cancel out. Yeah, so the increasing the temperature will increase the flux on the blue part, and then increasing the extinction will reduce the flux on the blue part again. Yeah, so we will come back to that later. Okay, so these are the basic observables. So now let's come to the what you actually have in the Gaia catalog. So, and here I'm referring to the Gaia archive. So of course, there are several mirrors of the Gaia archive in various different places around the world. But in principle, these are all very similar to the Gaia archive. Okay. So if you if you click on that link, it will take you to the Gaia archive. Then you go on search, and then you go on to this tab of ADQL queries, which is the preferred solution. Then you can see here what tables are available. And you can see, obviously, there are data release 1 and 2, and most recently, data release 3. And you can see here the two main catalog tables, which are Gaia Source and Gaia Source Lite. As the name suggests, Gaia Source Lite is just a light version of the first one. It doesn't have all the columns of the first one, but it has the most important columns, and it's therefore, because it's more lightweight, it's faster to query. And if I sorry, if I go back, if you click on this little plus here, this would open and show you what columns are available in each table. And I've done that for the Gaia Source Lite table. And I, in particular, want to show you these two columns here, which tell you whether a source has the XP coefficients and whether it has the XP sample spectra. Remember, these are in the external system that look like a proper SED. And then when you want to run queries, I will just very quickly show you how to get these XP spectra. So here, this is just a toy query. I'm just taking the first 10 objects from the Gaia source light table that have a continuous XP spectrum. And then you wait for this query to run through, and you get this hook here that it has finished. And so you would click on this symbol to download the actual query results. In this case, this would just be the source IDs. And then to get the XP spectra, you would click on this symbol here, the two interlinked chain elements. Yeah, and this is called data link. And when you click on that, a dialog window will pop open, and it will ask you what data you want. And there you can then select that you want the XP spectra for these 10 objects. Okay, what you also have in this in the Gaia archive is this tab here, the Astrophysical Parameters. And when you would click on this plus sign here, it would open. And there you can see two tables in there, the Astrophysical Parameters and the Astrophysical Parameters supplementary tables. And if you would open the lower one, you will see what columns are available in the Gaia archive. And for instance, you will see something like log G _ GSPPhot _ marks. And this is essentially now what we are going to talk about. These are the places where you can find astrophysical parameters, in particular the GSPPhot results. Okay, so now let's talk about GSPPhot in general and how it works before we then later on show you some scientific results. Okay, so having seen this before, this is just a reminder that the BPRP spectra contain a lot of information about the characteristics of the stars. So the goal of GSPPhot is to estimate the stellar parameters given the XP spectra. In particular, what GSPPhot tries to estimate are the effective temperature of the star, the surface gravity, the metallicity. Then, as I've shown you before, also extinction has a large impact. So GSPPhot also has to estimate the line of sight extinction, which comes in various different forms. So in principle, A0 is just the parameter of the extinction law, which just generally defines how strong is the extinction in that line of sight for this star. And then derived from that are the extinctions in the 3 Gaia bands, so the G band, the integrated BP, the integrated RP, and the reddening. So obviously you need these 4 if you want to plot color magnitude diagrams and de-redden them. Yeah, and these are obviously dependent on the SED of the star. So for a hot star, so even if you keep the actual extinction fixed, a hot star and a cool star will have different AG, ABP, ARP, because that depends on the details of the SED. Okay. And then also some fundamental parameters of the star, namely the absolute magnitude and the radius, and also the distance. GSPPhot doesn't only use the XP spectra for that. Of course, the XP spectra are the main thing that GSPPhot relies on, but GSPPhot also uses the parallax and the apparent G-band magnitude, as I will explain in a minute. In data release 3, GSPPhot has published results for 470 million stars, brighter than 19th magnitude. And usually you get several results per star. And the reason is that in order to model these XP spectra, we need model SEDs. However, these SED libraries that we typically have, they do not have cover the full temperature range. So what instead we do is we have 4 SED libraries, which all have different temperature ranges, and I'm listing them here. So for instance, one of the libraries we are using is the Marks library, which in the version that we have has a temperature coverage of 2,500 Kelvin to 8,000 Kelvin. And so, we have various other libraries, and I just want to point out that the hottest stars we can model are 55,000 Kelvin. So for each star, so each star is processed 4 times, once with each of these 4 libraries. So you get in principle 4 sets of results per star. What we then do is we recommend a best library according to which star achieves the highest posterior probability. In other words, which library achieves the best fit for each star. Now, these best library results are reported in the Astrophysical Parameters table, for instance, as temperature underscore GSPPhot. But because the way we identify the best library may not be ideal, you may have your favorite library, say you always prefer marks over everything else, or you do not trust, or you find a better criterion to select the best library. We also provide the 4 individual library results in the Astrophysical Parameters supplementary table. And this is what we've seen before. This would look then like something like log G underscore GSPPhot underscore marks, or something like A0, that's the extinction parameter, underscore GSPPhot underscore OB. And so this is the meaning of these different columns. So the default selection would be just to go into the astrophysical parameters and use the best library results. And if you find something weird, or you want to look into something very specific, you could then also explore the individual library results. Okay. So let's talk about the details of how GSPPhot works. So if you like, the mechanics of it. So one of the key tricks of GSPPhot is the following. So the model SEDs that we are using, they scale as, so the model scales as Boltzmann constant times the temperature to the 4th. Yeah, so this is just the way model SEDs are typically computed. Now, the key trick here is that the XP spectra are not normalized. They come with an absolute flux calibration, which means that the observed XP spectrum also scales with temperature to the 4th, and that's very important, it also scales with radius over distance square. So that means if GSPPhot can get a stellar radius, say from some isochrones, then we can fit for this amplitude of the XP spectrum given a model spectrum. And this amplitude will tell us immediately what the ratio of radius and distance is. And this is what I'm showing here on the right-hand side. These are GSPPhot results. So from this amplitude, if you take the square root of this amplitude and multiply it by 2, you get the angular diameter of the star. And if you compare that to ground-based measurements, you get a very tight correlation. So this radius over distance is very well constrained. And this is a characteristic of the XP spectra. Yeah. And GSPPhot is just exploiting that. All right. So how does that work in even more detail? So what GSPPhot does, it's an MCMC algorithm. And the actual fit parameters are the age of the star, the initial mass of the star, the metallicity, and the line of sight extinction. What GSPPhot then does, it takes an isochrone, a set of isochrone models, and given these parameters, it interpolates the isochrones, and it obtains the spectroscopic parameters from the isochrones, which are the temperature, the gravity, the radius, and the absolute magnitude. And then it takes the XP spectra and the model SED, say from marks that you can compute for these spectroscopic parameters, and then it estimates the distance as I've shown on the previous slide. So once it's gone through all these steps, GSPPhot then has all the parameters that it needs, and then it can compute a chi-square from fitting the XP spectrum. It can compute another chi-square from the parallax because GSPPhot has derived internally a distance. And it can also compute another chi-square from the apparent G magnitude, which is just the apparent magnitude, the absolute magnitude from the isochrone, the G band extinction from the line of sight extinction and the model SED that results from the spectroscopic parameters and the distance, obviously. And then the total combined chi-square is the sum of all these three chi-square values. And on top of that, because this is an MCMC, we need a log posterior. So having a chi-square, meaning a likelihood, is not enough. We also need priors. GSPPhot uses the GDR3 mock catalog, which is a simulation of what Gaia was supposed to see in data release 3, to build a Hertzsprung-Russell diagram, a distance prior, and an extinction prior. So essentially telling GSPPhot, okay, if you're a star at that distance, that should be that distance is so and so likely a priori. You should have a priori this kind of extinction and this kind of Hertzsprung-Russell diagram in this distance at this apparent magnitude. Okay. Now, this is how GSPPhot works. Now let's look at some results from data release 3. So the first thing that you can do, getting an extinction estimates for each individual star, you can just plot sky maps and just bin the stars together and just average in each bin on the sky, just average their extinctions. And here we have done this for the Cygnus X1 region. And on the left-hand side, this is GSPPhot results. And on the right-hand side, these are results from base star 19. And you can see that in general, the structures are, you see my mouse, right? In general, the structures are very similar with high and low extinction. What you can also see is that GSPPhot can reach slightly higher extinction than a base star. This is to some extent, as I mentioned before, temperature extinction degeneracy. So GSPPhot extinctions can be spuriously high. But there's also another issue here, the way that base star 19 works. Base star 19 averages the extinction over space. So in that sense, it can, because of this averaging process, it can wash out higher peaks. Yeah, so to some extent, the fact that GSPPhot has higher peaks than base star 19 can be is partially due to GSPPhot extinction sometimes being spuriously high, but it's also due to a base star 19 sometimes underestimating extinctions when you have very short scale, high peak extinctions. Okay. Another thing that you can use GSPPhot for is to plot typical diagrams of stars, like Hertzsprung-Russell diagram on the left-hand side and the Kiel diagram on the right-hand side. And in general, they look pretty okay. They will look better in the future, as I will show you later. But you can see certain artifacts here. And one of these artifacts is, for instance, this stripe here, this vertical stripe at 15,000 Kelvin. And you can also see it in the Kiel diagram on the right-hand side. And what that is, this is the lower boundary of the OB library grid that I mentioned before. Yeah, so this is the best library results that I'm showing you here. And for some reason, at the boundary grids, GSPPhot results can pile up. And this is what you're seeing here. Yeah, also, the other boundary grids are hidden in this data here, but they don't stand out that clearly. Okay. Here's another test that we did. So we compared the GSPPhot surface gravity estimates to astroseismic values. And as you can see here, for solar-like oscillators, so these are in red, these are red giant stars. And in blue, these are main sequence stars, which all of them have solar-like oscillations as measured by Kepler. And as you can see here, there's in general a very good agreement between GSPPhot and astroseismic measurements, which is kind of surprising if you consider the low resolution of the XP spectra. However, as the bottom panel shows you, GSPPhot tends to drastically underestimate the uncertainties. Yeah, so astroseismic gravity measurements are usually very, very precise and have negligible measurement errors compared to even spectroscopy, and definitely compared to XP-based log-G measurements. So we can safely assume that the only uncertainty is from GSPPhot here, so the random errors. whereas the random errors from the astroseismology side are totally negligible. So we can take the differences from the upper diagram and just divide them by GSPPhot's uncertainty measurement. And then we should see a unit Gaussian. Instead, what we see is a Gaussian, so this dashed line is a Gaussian with width 10, so it's 10 sigma. That means GSPPhot is underestimating the uncertainties by roughly a factor of 10. And we will also come back to that in a moment. So what I'm showing you here is a sky map by various different catalogs of the temperature residuals. And in general, the temperature residuals are pretty good. However, you can see some systematics. You can see that typically in the disk, so where the extinction is very high, GSPPhot tends to systematically overestimate temperatures. And that is, as I mentioned before, this is the temperature extinction degeneracy. And with this plot, I'm exploring this a little bit more. So what I'm using here is what our colleagues that produce the XP spectra have done. So they have provided a small sample of something like 50,000 stars, where, as I explained before, the mean XP spectra combine roughly 40 epoch spectra for each star. So what our colleagues have done is they have taken the 40 epoch spectra for each star in this subset, and they have randomly grouped them into two groups. Why random? Because if there's time variability or the instrument evolves or something, you don't want to take the first half and the second half. So they just randomly grouped them, all epoch spectra, into two groups. And then they computed for each star two mean spectra, one mean spectrum for each group. And what that allows you to do is you get two statistically independent noise realizations of the same XP spectrum. So you can use this to validate your uncertainty estimates. Our colleagues have done that to validate their XP uncertainties, and we have been using that to validate our GSPPhot uncertainties. And in this particular case, because both spectra belong to the exact same star, they should have the same temperature and the exact same extinction. And this is what I'm plotting here. So that just the temperature and extinction differences. And as you can see, you have degeneracies here. Yeah, so this gives you a direct handle on, or a direct visualization of the temperature extinction degeneracy. And it's color-coded by the surface gravity. So you can see that for dwarfs, the temperature extinction degeneracy looks different than for giants. In particular, for dwarfs, you can easily have 500 Kelvin errors due to the temperature extinction degeneracy. Okay.
Hi, Renee. Sorry to bother. It's
yes?
9:45, just to give you a mark of the time.
Yes, okay. Sorry, you also had an introduction. Okay. Very quickly, you can also use these split sources to quantify how much the uncertainties are underestimated. And if you do that, you find typical factors of 1.6 for the distance to 3.5 for the metallicity. Yeah. Other issues that we found during the validation is that we systematically underestimate the distances with GSPPhot for stars that have low parallax quality. And we very quickly figured out that this was due to an overly harsh distance prior that we used. So this will be fixed in the future. That's very easy. There are also a sizable fraction of outliers in the GSPPhot results, which we traced back to the poor initialization of the MCMC. So the MCMC did converge in these cases, but it converged to the wrong solution. Yeah. And one main limitation of GSPPhot in data release 3 is that the metallicities that GSPPhot estimates are heavily biased to an extent where I, as the GSPPhot person, will tell you, do not use the metallicities from GSPPhot in data release 3. The reason for this was that the model SEDs we are using do not really match the real BPRP spectra, because our understanding of the BPRP instrument isn't perfect at this stage. And I'm just showing you this here on the right-hand side for a solar twin. So if we just look at the BP side here on the left, this is a solar twin and various models of the solar twin that are color-coded here. And as you can see, the different models produce very different predictions, and none of these predictions really matches the data. And the gray contours show you, yes, this is easily detectable in BPRP. Yeah, so we very early suspected that this problem with the metallicities is due to this model mismatch, and in work following data release 3, where we estimate metallicities empirically from XP spectra, we have shown, yes, XP spectra do contain a lot of metallicity information if you work empirically. Yeah, so that's not a limitation of the XP spectra. I will skip the last point in the interest of time. Okay, so very quickly, what are the next steps for GSPPhot? So obviously, GSPPhot will also run in data release 4. And we have implemented several improvements following data release 3. Most importantly, we've now used a better distance prior, so this problem with the underestimated distances is now fixed. We also improved the initial guess for the MCMC, so we get the rate of outliers is much reduced. And then some other details like we improved the way we interpolate over isochrones. We empirically recalibrated the models we are using in order to compensate for their mismatches. Then another very important change is that we use the full XP covariance. So I haven't mentioned this before. The XP spectra, they have correlated pixel fluxes, so they are not independent. And in principle, you need to take this into account. And of course, in data release 4, we will get better XP spectra, better XP models, and also better parallaxes, which GSPPhot is also using. But I can already tell you, you won't have to wait for data release 4. So we are currently preparing a reprocessing of all the published 220 million XP spectra. And this will be published also very soon, ideally within this year, which will bring all these improvements, except, of course, the data release 4 XP spectra will not be included there. All right. Very quickly, just to show you some difference between the DR3 version of GSPPhot and the latest versions with all the improvements. So this is a color magnitude diagram, de-reddened. And as you can see on the left-hand side, we still had quite a few issues with spurious solutions here in this part of the diagram, which is now fixed. So the right-hand side looks much better, much more physical. I should also say, all these comparisons are always the exact same selection of stars. Yeah, so we are comparing apples and apples here. Here, this is just to show that the distances have been fixed. So we compare distances to parallaxes. So we get this negative relation here, which is just 1 over parallax. And by eye, you mostly see it in the signal to noise ratio distribution that it's improved, but the number statistics, so the root mean square difference shows the largest improvement. This is just to show that this empirical recalibration of the models fixes the metallicity issue. So in data release 3, we had this, in general, this systematic offset here, and also these weird outliers here. This is now fixed. Yeah, so the bulk of stars is on the 1-to-1 relation down to metallicities of -0.2. Astroseismic gravities are also, I mean, they were already very good before, but now they're even better than before. Yeah, so that brings me to my last slide. Yeah, so just as definition, what is GSPPhot, such that you can tell apart the different work packages. GSPPhot tries to parameterize the stars from the XP spectra, apparent G magnitude, and parallaxes. In data release 3, we had 470 million results, which can be found in the Gaia archive in the Astrophysical Parameters table. The main limitations of the GSPPhot results are: don't use the metallicities. Be careful with the distances. They can be too small for low quality parallaxes. Then there can be outliers at, I think, 1% rate or so, or even slightly lower than that. And obviously also the uncertainties are systematically too small. And this will also be the case for the reprocessed GSPPhot results, which will hopefully come very soon. Okay, thank you for your attention.